Okay, so in this last series of videos, we're going to be taking a look at the dynamics of oscillating systems. We'll start by revisiting the simple harmonic oscillator briefly, work to coupled harmonic oscillators, then eventually work out to the wave equation. So first we'll start by taking a look at the stability of a oscillating system. So let's start by taking a look at some one-dimensional conservative system. Let's say we got a mass on a spring. So there's the equilibrium position for our mass M. Like so. If I move it over here to some position X, it will feel a restoring force F that brings it back. Okay, so we can write the potential energy of that system as a function of the distance from equilibrium as 1/2 kx squared. And so the restoring force would be equal to minus dv dx is minus kx. All right, so if I were to plot the potential as a function of the displacement away, the way I would interpret this, I'll have a nice parabola here for my v of x, like so. And so say if I'm displaced off to the right, I take a look here and I have a positive slope. So if I have a positive slope, because the force will be the negative, that means that my restoring force anywhere to the right will be pointing into the left. By the same token, say if I'm over here somewhere, here I'll have a negative slope. So there we go. So again, the force being the negative of that negative would be positive, which means that the restoring force would be pointing to the right. Okay. So in the neighborhood of the equilibrium position, if I displace off a small bit one way or the other, the restoring force will seek to return us back to the equilibrium position. And so this is a hallmark of a stable equilibrium. All right, so let's take a look at a slightly more complicated example. We can go and revisit the pendulum. So there we go. We got mass M there. And we have two forces acting out. We've got the tension like so, gravity like so, and our displacement off of equilibrium is angle theta. So the potential energy will be given by mgl times 1 minus cos theta if we pick the bottom of the swing as our v equals 0. So following our prescription for generalized forces, the torque the restoring torque in this case will be our generalized force, and we get that by differentiating v with respect to theta. And we get minus mgl sine theta. All right, so how do we test the stability of that? Well, we can go ahead and do a Taylor expansion, more properly a Maclaurin expansion since it's about 0. So sine theta becomes theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus and plus and so forth. All right. But if we're near equilibrium, which is all we are really concerned about, is seeing if the equilibrium point is stable, we can drop the higher order terms because theta is already going to be small, so theta cubed will be really small, theta to the 5th is absurdly small, and so forth. We get minus mgl times theta, which is in similar form to our minus kx restoring force that we had for the mass on the spring. It's minus some stuff times our generalized coordinate. Okay, so that's a restoring force 2. All right, so this gives us some sort of a clue here. If our potential energy function near equilibrium, so these are types of equilibrium here. So if near equilibrium, it looks like some sort of parabola-ish kind of thing as a function of our generalized coordinate. We'll deem that to be a stable equilibrium. On the other hand, if instead of holding water, we spill water, like so, well then here the slope would be positive, it would be negative, so the restoring force would be positive. So we'd actually be, if I nudge it here, we'd actually be running away. So if I put it right perfectly at equilibrium and don't breathe, it'll stay there. But if I breathe or let it quantum fluctuate or whatever, it's going to run away. So we'll call that an unstable equilibrium there, because it won't want to return back. There is an intermediate possibility, and that's just that the potential is a constant around the equilibrium area. If that's the case, we'll call that a neutral equilibrium, because it just kind of sits in between stable and unstable. If I nudge it away, it'll run away, but it'll run away at constant speed, versus here it'll run away accelerating. All right, so that handles most of our cases, but there's one more case we do need to look at, and that's like, let's say our potential or instead look at something like, say, 1/3 kx cubed. All right then. So if I plot that, VQ, like so. Suppose I should call the generalized coordinate x here, since I gave it a name. All right, so if I plot that, now I got a bit of an issue. If I look over here, the slope everywhere except right here the slope is 0. But everywhere else, we look at this and we realize that the slope is positive, which means that everywhere away from equilibrium, the restoring force, or I should just say the force, is to the left. So to the right, it would be restoring. So that sounds good, right? You displace off to the right, it restores to the right, but oops, as soon as we roll through the equilibrium point, now the force is off to the left, and we speed up and we run away. We can see that if we went ahead and calculate the force, minus dv dx would be minus kx squared. So we can see at best it's 0 at the equilibrium position, and anywhere else it points to the left. So this is actually also an example of an unstable equilibrium. So the moral of the story is that to have a stable equilibrium, without loss of generality, we can set, just make the discussion make sense, we can set the potential at equilibrium to be 0, right? That's just by shifting the, by adding or subtracting a constant. So then do a series expansion. And then we want to look at the leading term. If the leading term is an even power and positive, then we have stable equilibrium. All right, so that's our test. All right, so let's expand this thought. What if we have more than one degree of freedom? Let's say we have n degrees of freedom. We're still going to require that our generalized forces vanish. At equilibrium. So our generalized forces will be the derivative of our potential, which will be a function of our n generalized coordinates, right? And we would be differentiating that, strictly speaking, a minus, but it's not going to matter because we're going to set to 0. And we differentiate that with respect to each of our generalized coordinates. So we demand that all of those partial derivatives for k equals 1 to n be 0. So again, like I say, minus sign not a big deal because we just plain need the, in fact I'll just put in parentheses here, so we just plain need the derivative to vanish to make that happen. Alright then, so we've caught on that we need the leading term in our expansion be an even power and positive. So that means we need to, usually we'll need to focus on the quadratic term. And it's going to be really rare that you have a situation where you don't have a quadratic term in your expansion. So we'll just focus on that. So our quadratic term for V is going to look something like V of our Q1 to Qn will equal 1/2. And then we're going to just have a whole bunch of coupling constants, which we can't really call them spring constants anymore because they might not be springs. We'll call them coupling constants. So first one we'll call K11, and that'll be times Q1 squared. Now we could also have a possibility of, say, we'll have we'll write it as a 2K12 Q1, Q2, because it's possible that two elements are connected together by something, plus K22, Q2 squared, plus and so forth. Again, here we're setting the potential at equilibrium to be 0. And so here, if I go ahead and expand, the linear term would be 0, and so the quadratic term would be the first thing that contributes. So we'll have stability, says linear algebra, if the determinant of our coupling constant matrix, K11, K12, da da da, K21, da da da, K22, da da da, like that. If that determinant is greater than 0, that's our test for stability. Okay, so in the next video we'll go ahead and go on with this a little further by exploring the oscillation of a system with 1 degree of freedom.